There's some terms I just added this morning because we're looking at plugging there. Reversing is changing that motor's direction of rotation. So it don't mean forward and reverse. Sometimes it might be up, down, or some other types of slide it off in some direction. Jogging, we already talked about this. This is run the motor short burst, usually position and object. Plugging, changing the direction of the motor without allowing the motor to come to a complete stop. This is not good on the motor. So normally, especially if it's not a button, somebody's got to take the patient first, how long does that take? While it's running. So, it's only pulling that starting current the whole time, right? And so that little limit time, when you just start the motor, we're trying to pull that starting current the whole time while it's trying to reverse all up. Change the direction of the motor without allowing the motor to come to a complete stop. Interlocks, preventing the two directional contactors from energizing at the same time, creating a short circuit. We're going to look at two types. We have mechanical interlocks. Well, in this class, and I can't find, we got a motor starter, we got a reversing contactor somewhere that has the mechanical interlocks on it, but for some reason, the circuit disappeared. I don't know what somebody would do about that. In our lab, we're going to use electrical interlocks. Contactors, these are a relay that has contacts in the power circuit of the control system. They can also have contacts in the control system, but we call, I need to put that, these are auxiliary contacts. So auxiliary contacts, we're in auxiliary contacts from motor starters and contacts. These are usually lower voltage ratings, they're usually lower power current ratings, usually strapped on the side of the side. So we're looking through auxiliary contacts on it. This one is so magnetic motor, a manual motor starter, this is a device that contains overload sensors that is changed, the contacts are changed manually. I need to reword that. So, and yours is a lot bigger than that. The overloads on this one, these are electronic overloads or magnetic overloads. These, you don't have to change the heaters. We talk about the different types, right? And, I don't know about that. That's over here. A magnetic motor starter, this is a device that contains overload sensors that are used to change the contact position. It uses a coil to change the contact positions, right? This is not covered very well in the circuit. These are jog circuits. No, that first one's not a jog circuit. That's just a regular. Let's see if I can find that again. Got these off the internet. Motor. Or up in one of your labs. So the second one is the one you'll do. You'll use the selector switch. Our selector switch is a three-positional selector switch. So we'll just you can use manual or auto. It don't make any difference. And then off to break the sealing system. So on this one, if we put it in this one, if we put it in jog, it closes this contact but opens that contact, right? You know, and then now when I press the start button, it won't seal in. If I put it in run, then it closes this normally closed contact and opens this normally open contact. And now when I push start, it's going to seal in. Okay. By the way, we're having problems with symbols. You're being graded on using correct symbols. If you come over here and because your drawings are going to be used by other people. So if you come over here and you draw a normally stop push button like that, then technically that would be called a normally open held closed. So on your start button, it allows them to get really close together too. It goes on the top. This is a normally open push button. And then your stop button goes under the bottom. Okay. So y'all understand that? So there was somebody that drew them wrong. There's another big quirk I've got about that. When you put the unit number, when you put the chapter number, you just put like an S. You don't put an S-23 to tell me it's on page 23. I don't need to know that. So we got two people in the class that's doing that. And now you get me confused. So you put S-2 and then over here you got experiment number 1, right? Understand that? So that unit over there where it asks you the chapter number, you just put one little thing out there, right? You understand that? You put an S, you put an SF, you put an LD. Don't include the page number. I don't need the page number. You just confuse Rich. You add a little time to my grading, right? So I got some of these I'm going to give you all a reprieve on. But from now on, if you put the page number inside where I'm asking for the chapter abbreviation, if you put a page number, I'm going to take off points because it adds to my, I got to figure out, right? Understand? To you, adding a second or two means nothing, but I'll show you all the stack of papers I end up at the end of the term. And if you add 1 second to my time, you're actually adding minutes to my grading time, right? Understand that? Another big problem we have with labs is people not putting their name on the title page. One person didn't even put the title page in there, right? Left pages out. You got 2 problems with that, right? Understand that. So I'll give these back to you and let you make corrections for me. And this will be the last time. After that, I'll just start grading off. If you don't include the questions and you leave them out. So I had one guy put 1 page in there of about a 5-page thing. Put 1 page in there. So they left out a bunch of stuff. Somebody put the entry page to the discussions and they didn't put the actual first page of the experiment. So I'm going to show you that. So, manual motor starters, y'all see that? Manual reversers. We don't have a manual reverser in here. So basically what we do is we have 2 sets, separate sets of contacts. This would be 3-phase. So what we would do is we would have 1 set controlled by one side, and then we'd have another set controlled by the other one. So over here, if you push forward, if these were all F, then all these would open. I mean, all these would do what? They would close, and these over here would open. If you push reverse, then these would close, and then these would open. So these are mechanically interlocked with each other. And it will not let you push forward and reverse at the same time. So these are mechanically interlocked. So these are manual motor starters. What advantage does a manual motor starter have over a magnetic motor starter? Not much. These don't, if you're going to control it with a control system, the odds are you're going to have to magnetic motor starter. But if you just got one thing where you're stopping and reversing the motor, you're not running to a control system. That's the only thing on that odds are they're going to do that. So basically what we do, we'll have to show y'all that. Mechanical interlocks devices are inserted between. Now the problem we have, if your forward and reverse contacts closed, so we never want to allow that to happen. So we're going to interlock. Interlock is going to select forward, they're going to mechanical or whatever. So here, mechanical interlocks, which means we got dash lines that indicate that these are mechanically connected together. And what that tells us is that you cannot do what? So if you press the reverse, what's going to happen? It's going to kick out the forward for you, and it's going to run the reverse. We have a little problem with this. What's the problem with this one? These guys. We got no option for them. What happens to those? It's reverse. On club, right? So there's no hard to that. So here we can make sure we have a motor that's got a service factor on it. We don't plug motors that got a service factor of 1. So they're not designed to overclock, right? You got a service factor of like 1.25, the motors probably the same component. And I wouldn't put it off. This one you have to. Unless you had another something that killed power out here. Oh yeah, these cannot be plugged. I'm sorry. You're right. I just noticed that. Thank you, Kat. So on these, we wouldn't hit what? We wouldn't hit these buttons. What would we hit first? Stop, yeah. So a lot of the plugging circuits are manually taken care of, which means it's up to you to not plug those. It's like the signal thing. It's up to you to not plug that motor, right? So what should you do when you want to change direction? Understand that. Yeah, stop it first, right? And then let it come by. Stop and then reverse it first. Okay, well, do that. It's kind of hard to do. Not on the side. That's signal thing? Yeah, so it's on the side. Yeah, but you can put your arm up there and get hit by the thing. Not all mine. I don't know about mine.
All mine are above the blade.
Oh, really?
Yeah.
Of course, I've got 2 that are radio controlled. But all my other ones, of course, I've had mine for a long time. I didn't know that, guys. So this is the way we reverse a 3-phase motor. And what are these the symbols for? Overload sensors. So overload consists of 2 things. It consists of the sensor that sensors the overcurrent over time, and then it's got an overload contact that's in your control circuit. So this is the actual sensor. So what we do, and this is already here, the way we reverse a 3-phase motor is we swap any 2 leads. If you swap any 2 leads, then the motor will reverse. So if you can do it 3 different ways, and what they did is they came up with 2 ways that were going to reverse. If you do it this way, the person that follows will understand the way it should be done. Right? So what we do, the industry standard for reversing a 3-phase motor is L1 and L3. Let's get this happen. So let's close the forward contact. And of course, when we close the forward contact, then I'm going to take L1 and connect it to T1, L2 and connect it to T2, and L3 connected to T3. So the motor's going to run in a direction that we're going to call forward. But it could actually be up, down, left, right. Y'all understand that? Okay. Now when I come up here and bring in the reverse, not at the same time, we'll show you why we're going to do this. So here we come up here. Now these contacts are going to close. Now I'm going to take L1 and it's going to go to T3. Then it's going to take L2 and it's going to go to T2. And it's going to take L3 and then it's going to switch it over to T1. So we just reversed that, right? Now the problem is if you let both these come in at the same time, then what happens is I'm going to take L1 is going to connect to L3. That's a short circuit. We don't have any problem with this one, but But L3 is going to connect to L2, L1, and that's a short circuit. So we want to make sure that these guys right here never come in at the same time. We don't want to give it that capability, right? Everybody, we don't want to leave it up to an operator that has the ability to press a forward button and a reverse button and have both of them come in at the same time. And this is where the interlocks come into play. When using a manual reverse or starter reverse three-phase, L1 is connected to T1, L2 is connected to T2, L3. Now this is a relative term. I've seen a lot of companies don't know the phases. What they'll do is they'll just pick up the motor, right? They'll show that, see what's the pressure of them. And they use that to identify, and they'll identify an L1, L2, L3. And they'll know they need to reverse, right? I think they have a lot of them. And then some companies do identify the three phases. And they have what they call a phase rotation meter. They can actually put on it to see which ones are which. Single phase motors, what we do is we swap the start line. So that's the industry standard way to reverse a single phase motor is to swap the start winding. Some of them are non-reversible, like the one over here. This one, if you look at the actual thing right here, see they have a start line available. Right now, okay, they go 2 wires off on that door. So normal way to reverse a single phase motor is to reverse the what? The connection on the start winding. If you reverse both of them, it'll run in the same direction. It won't change direction. You have to change the relationship between the two fields. Everybody okay? So we could trace this through. You want to trace it through? So let's go forward. Close these 3 contacts. And this would come up here. Can't go that way. That's an open circuit. Goes through my overload sensor. Comes through. This is the run winding. And this goes back to L2. Here's L2. So let's see. Here's L1. It comes down and goes to the start winding. So here's L1 right here. And what's that a symbol for? Spell this right. Centrifugal, C-A-L, centrifugal switch. So on these motors, the only thing we need to start winding for, is called a start winding, because it's only started. But here's the cowboy right here. What happens is he goes up, he's pulling out, causes the plank to go down like that, and then it disconnects the switch. Well, this doesn't keep that start line. So once the motor is started, and the phase shift is in there, this is created by the rotor. This one looks like it's a split phase motor, but it doesn't really make any difference. Be transparent to us. Then somehow we got to get this guy back to L2. So it's back to L2. So this guy right here is going to what? L2. Now, of course, when I switch them, we should see L2 come up here. This is going to stay the same down here, right? You understand? The run winding, so this is referred to as the run winding. This is referred to as the start winding. around the place. What I'm gonna do is I'm gonna come up here and erase most of this, because I'm just gonna leave the L1 and L2 on my start winding. And I should have left it on the run winding, but it'll be the same. You notice the run winding actually goes back to L2. It didn't go to a contact. So it means the other side's always got it. So on my run winding, this side right here will always be L2. So it means this guy right here is going to always be L1, right? So this is L1. So I'm going to change colors. We'll go to blue. We'll close these contacts right here. Now L1 is going to go to this set of contacts. So right off the bat, we see before it was what? L2, now it's what? L1. We could trace them all through again, guys. We come up here. It comes up here, connects there. This is my run wounding. This is L2 now. We can trace this one too. This one goes back. It goes to L2. And then this one goes down and brings the L1 back to my run line. So how do we reverse a single phase motor? What's the industry standard for reversing a single phase motor? Unwind or start one. Nobody's passed those until I got it out. Think this is going to be on the test. Or do you think? What do you think?
I think it'll be on the test, for sure.
On the single phase motor, so what's the industry standard for reversing a three phase motor? Okay. What's the industry standard for reversing a single phase motor?
I still don't get this, because I don't know what I'm swapping.
Well, notice the first time I ran this winding right here, it came up to be L2. The second time I rounded, it came up to be what? L1. The first time I did it, it was L1. Now it's what? It's L2. When I go back to the run winding, it can't swap, because if you look, if we go back to the run winding, one side is always connected to L2. So when I look at this winding right here, this winding right here, it does not go to a contact. It always goes back to what? L2. And if I look at this winding right here, in the forward direction, it goes to L1, right? You understand that? And in the reverse direction, if I swallow this winding back up, in the reverse direction, it comes up and goes through this set of contacts and goes back to L1. So no matter whether the forward or reverse is in, the run winding is hooked up exactly the same way. So it means we're not reversing the run winding. We're reversing the what? Start winding. So the industry standard way. So the first time I came up here, I said this was L1. The second time was what? L2. Over here, the first time was L2. The second time was L1. So what we're doing is we're reversing the direction of the start line. So the industry standard method of reversing a single phase motor is to change the start line. Is that a acid motor, is that a split-phase motor, is that a universal motor, it's all of them. Change to what? Start one. That's the way, you could change one line and do the same thing, but that is not the industry standard way. And the problem is, if you don't do that according to the industry standards, then the person that comes out after you is going to frustrate you a lot. Number one, because you didn't do it right? Well, it worked, right? If I don't follow it worked, then all they do. I saw you use, I said, the ground wire, the solid, the one uninsulated wire, I saw him use that as solid. Because he didn't have a 40, he didn't have a 3-wire, like 40, he had 2-wire with the ground. He was just electric water heater, and he used a 3-wire and what he used. It worked.
Yes.
So they didn't touch it.
Yeah.
So, he was an interesting fellow. I loved him to death. He was funny too. This shows you the 2 circuits, by the way. We just drew that out. This is a DC motor. So we got 2 things on the DC motor. We got what we call the field. Stationary field. Some people misidentified it as stator. Technically, stator and rotors are for AC motors. Field and armature are for DC motors. So what we do on here, we have 2 connections we can make. We can make that. We change the connection on the armature, or we change the connection on the field. What do you think you can do? Armature. Why is that? Just kidding. The problem we have with, especially shunt motors, is that if you lose the connection on the field, the motor comes up. Because it's trying to create countering and all this kind of remains. So the indicator what method of reversing the DC motor is the shunt on. You could say that on a permanent magnet motor. But permanent magnet motor, and what you want to do, you want to do all motors the same, right? Permanent magnet motors, you can't change the field without taking the magnet apart and changing the magnet on the top. So all DC motors, the standard is reverse the connection on the armature. But you notice it still uses the same, basically the same circuit. So what I'm going to show you guys is the circuit that reverses motors are about. They're going to always find the DC motor, an AC motor, single-phase motor, 3-phase motor. Don't make a difference. The circuit that reverses something, reversing circuit, a legal reversing circuit that prevents don't prevent flooding. We can still flood the motor if we have to, right? Sometimes that has to happen. But it's up to the operator to confirm if it's flooded or not. If we want to prevent flooding altogether, we'll add another device called anti-flooding pressure. We'll see how that works. So this right here would not allow you to energize forward if the motor stop and reverse direction. This would require a sub-shaft motor, so you have to have a shaft on the side, underrun the flooding. So plugging the motor basically is up to you. But you got to realize, I've seen people plug a motor and it kicks the overload out. Just to save a couple of minutes. Like people running red lights, right, to save a few minutes. Shunt motors, these are all in your book. What we need to know in this class is not to figure this out. What we need to know is the industry standard. And if you need to wire the motor, you can find all this information on my, I'm coming to platform site. I'm not gonna go through all of the first part. What's the industry standard way of reversing and repay mode? L1 and L3. What's the industry standard way of reversing a single phase mode? Or my swap with on the start line. What's the industry standard way of reversing a same line on? What happens if you change both the field and all the motor? There's you gotta change the relationship between the two. Motors over here, we can show you all that. The book covers all the circuits. This is a permanent magnet motor. This is a manual reverser. This is called a drum switch. You got one for you. It's at the center off switch. That's for each leg, right? So what you should do is go reverse the forward, you go stop, away from the other stop, or you can go. But you can't let these together. They play motors all the time, right? This is also another when we run into these, all you're going to do is run the motor forward and reverse. Odds are you're going to either one switch or you can use the manual motor starter. These guys right here are very simple, very cheap, right? You can't plug the motor if you have to. Now you have to remember this is going to be mounted in a solid piece of metal. We still run into a lot of these. Especially if all you're going to do is reverse the motor. If you're not going to turn it over to automated control, right? Automated control means we're going to run the system a little okay? And I keep walking away from my PowerPoint. This the book shows you the connections of drum switches. But you got to understand this information should be provided with the switch. So going over here is okay, but you know you might get out there and get a different drum switch that has different numbers on it. So what you got to remember is that it's going to reverse something, right? So we don't really need to go over trace these things through. This is a wiring diagram. It's not a real good one. They got a really good one. So what's the difference on a wiring diagram? Is the wiring diagram tries to orient or physically place the symbols on where they're at in the circuit, right? So here they're showing the coil on top of the what? L2. They got a really good example on back in here. So this is a standard reversing circuit. So here we're using against a forward and reverse contactor for coming in at the same time. We're using what we call mechanical interlocks. Let me find it all the way down this table. So this is a reverser mechanical interlock. And that's what this bar is across the top. So we can force these things by pushing in on here. So if I push on this one, that close the contacts on this one. But if I come over here and try to push this one up, guess what? Can't do it, right? So when I push this one in, then I can't push this one up. So these mechanical interlocks. What happens if the forward and reverse come in at the same time? It's going to create a short circuit. So you will, hopefully, you will not see a reversing circuit. That's not how. So can this circuit be plugged? Can we plug the motor with this circuit? Yes, so. Huh? Well, what if I hit this button right here and this closes right here, and then of course I'll let the button go. I hit the stop button, hit the reverse before the motor has the time to stop. Yes, we can plug. Yeah, we can plug this one. So what we're saying, most of these reversing circuits, plug the motor. So what you do is stop, and do what? Wait till it stops and reverse. Everybody see how this works? Pretty simple, right? So right now, even if I came over here and pressed this button, if I press this button and this seals in, which would cause this right here to seal in, and then it goes over here. Even if I do try to press that one, this guy can't switch positions, right? You understand, because of the mechanical interlock. But what you're doing is you're depending solely on the mechanical interlock, which is held together with screws and stuff like that. So if something happened and the mechanical interlock fell off, that bar that goes between the two relays, then that could cause a problem. So mechanical interlocks, are they foolproof? No. Everybody okay? That makes sense. So the other method that we use is what we call electrical interlock. So I'll come over and press the start button up here. So notice this contact belongs to this relay, and this contact belongs to that relay. So if I press forward, right, that's going to come through the stop button. It's going to come over here, hit the forward, right? It's going to seal it in. So now we have a backup right here, but it's going to open that contact right there. So if you come over and hit the reverse, nothing's going to happen, right? So how would I run it in the opposite direction? I'd hit the what? Stop, which would come up here and open that contact. So we go back to this, right? Then hopefully I come up here and touch the reverse, just hit it. It'll come over here. The forward's not running anymore. It'll pull in R, reverse, which should open that contact, and now I cannot energize the forward. So this is the best thing. This is the best way to do it, to have both what? Mechanical and electrical interlocks. So these are mechanical interlocks, and these are electrical. So you got a backup for the backup, right? That makes sense. Can we plug this? Sure, we can plug this, right? If we hit the stop button and then we hit the reverse before the motor has time, or change direction before the motor has time to stop. And this is what we're talking about. Most of these reversing circuits, once I've got reverse on the side of the electric.
Yeah, mine are all over the place. Yeah, stop first. Reverse.
This one, we're interlocking our push buttons. So we have the ability to do this. We have a start-stop station that has a single pole double throw, right? Oh, this would be normally open. So what we do here is these are mechanical. So I would wire this one in the forward, then I would wire this one in the reverse. That makes sense? So these are interlocked these ways, so the push button. So when I hit the reverse, what's that gonna do? When I stop the reverse, that's gonna close this one right here. Now, that would definitely plug it, right? Yeah. So, before you change direction, normally what we would try to do is do what? Hit stop, press this one, and then, let it stop, press stop, right? And then let it stop and then press one of these to come in and bring it in. Are we okay? So we have the ability to wire this one up. Electrical interlocks, mechanical interlocks. Y'all understand the difference? We don't have the ability to wire mechanical interlocks, so when we wire a reversing circuit, we're definitely going to use electrical interlocks. Are we okay? This is basically the same circuit. This is just showing you the connection. So with this circuit, what type of motor would this circuit, any of these circuits, what type of circuit, what type of motor would these reverse? Three-phase, single-phase, DC? Sure, all of them, yeah. So this is what we're talking about, the reversing circuit is the same. How you wire the contact. How you wire the contact. So if we're doing a single phase motor, we'll wire the contacts, not change the run line, you can change the start line. If we're using a three-phase motor, which we're going to be using in this class, we'll wire the contacts, swap L1 and L3 and not swap L2, right? Understand that. We're also going to wire it with all the power when you get stopped. So y'all notice every one of those circuits requires three contacts. So not only do you swap the lead, you also remove power from the start line and the run line or the DC motor. It's remove power from the field and on. This is the current angle. That one has an option on that. The circuit itself is basically the same. This guy right here adds, basically it uses the mechanical interlocks here, mechanical interlocks here, electrical interlocks here. So we got three different interlocks that will prevent these forward and reverse from coming in at the same time. What do we added to the circuit? We added an over travel limit switch. That means you run it forward, and when it hits the limit, it should open the forward. And then when you run it in reverse, it should run it and hit the limit. Make sense? Everybody understand how this works and follow that? This guy's got three types of interlocks on here. Mechanically interlocked push button, mechanically interlocking the vehicles themselves, and then you have electrical. Questions on this? Here's that question. And also they've added lights indicating the direction of the motor. We called it a reversing circuit, guys, and here every one of them they say forward and reverse, but you got to understand the direction of the motor is relative to its application, right? It's a reversing circuit, so those switches might be labeled off. Up, down, left, right, in, out, right, forward and reverse. If you label it the way the circuit itself would be the same, how, how, what the motor's actually doing. And forward and reverse is a relative term. So clockwise or counterclockwise, which one's forward, which one's reverse? Depends on where you're running, right? If you're running to a gearbox and stuff like that, you want to hook it up so the gear on the outside turns in the right direction that you consider to be forward. So clockwise, counterclockwise, that means nothing. It's up to the application of the motor, which one is considered forward, which one is Limit switches may be used to provide automatic control of a reversing circuit. You've seen this used a lot. Here the motors will plug. So what happens when it hits the forward limit, it'll do what? Automatically open. We can close this one, which can cause the motor to run in reverse. And I've seen this done before. We had a, what do they call it? Peel off valve off the top of the spring. And that thing, hit on that thing. Good, great. Probably probably about half the size. That's like from back. I'm not saying you can't put them right. What consideration would you take for number one, you're service. You don't want to put them up there, you know, that number's not designed to go over. And I see them plug. Like I said, cranes, they do that a lot, to make the load. So the crane's moving down the house and the load has to be in their pocket going forward, right? So they actually plug the load and try to stop it, you know, dodge it. Yeah, I never got that. Of course, so I wasn't a crane operator, but we worked on the controls that ran the crane. So quite a few of the cranes out there were radio controlled. So the operator just had a little transmitter on his belly. Limit switches may be used in a circuit to provide over travel protection, which is the same circuit they got. So we've lost our what? The only protection the only interlocks we have in this circuit is what? Electrical. Yeah, we got electrical. And how many people are going to do this right? So this contact is being controlled by this relay, and this contact is being controlled by that relay. And you tell people, when I come over and check it, the only thing I check is on one side. Find this class, don't hit that button. What's happening is you put it normally open, normally closed, forward, it's a forward circuit. So when it energizes, it's going to open. Then it's open, it's going to close. Everybody's going to look at it and laugh, right? We know what you did. This is a forward and reverse circuit. This one will not jog. I mean, not jog. This will not plug. You understand why? So we got a selector switch or a drum switch out here. We switched it in reverse. Then I hit the start button. A reverse will seal it into the bottom contact. And then I come over here and move it to forward. As soon as I move it away, then what's going to happen? It's going to break the circuit, drop the seal in. I guess you could plug it if you hit the start fast enough. Yeah, you could. And so all we're just looking at different methods of forward and reverse, and so this is one method. This has got a jog circuit built into it. So notice we have a unit that breaks the seal in. So both our seal ends run through this guy right here. So right now it's in the jog position. So if I press the start, if I press the forward, it won't energize this guy, which won't seal in, right? If I press the reverse, it'll energize this guy, but it won't seal in. So this is a very popular circuit. You see, we jog motors all the time. So what's jogging?
Control to run that motor a little bit,
Yeah, usually we usually do it to position something to
Yeah.
get in a start position or something like that. The plugging is,
Start the motor one direction, we're running the other,
yeah,
you're losing the other.
yeah, we're changing the direction of the motor without it coming in a complete stop. PLC, anybody know what PLC stands for? And what is a PLC? That's a computer. But it's specifically designed to run a primary language. So computers programming in a language. There's 5 available. Primary programming language for PLC, something called ladder. Now, this thing about a PLC, number one, is programmable. I mean, in a motor control, you change the circuit, you really have to go out there and rewire it. Only on the PLC, what you change the program. Plus, it eliminates all your control. What's a control? We've got 3 categories of relays. We've got control relays, we've got contactors, or found contactors. That's our sheet, right? And the contact. Get off the phone. Want to test it's okay for me, go out in the hall, I think, this is the motor control. Magnetic motor control. And this is the control relay. So contactors and motor starters are designed to have contacts in the power circuit. A control relay, all the control relays contacts are in the control circuit. A control relay has no contacts that's in the power circuit. So a control relay is not going to handle a lot of current. It's not going to handle a lot of power because all its intent in life is to control. Right? You understand that? A contactor will have contacts in the power circuit, and it may have auxiliary contacts in the control circuit. So this contactor is a really good example. You can see the auxiliary contact strapped onto the side. A motor starter, a magnetic motor starter, is a relay that has overload. A magnetic motor starter is definitely, its contacts are definitely going to be in the power circuit. It might have some auxiliary contacts that are in the control circuit. So those are relatives. In any control system, 90% of the circuit is control. In the PLC, at least 90% of the circuit can be a program. Other 10% is not in your power. But what you're done is you eliminated 90% of your relay. If you ever go into something that's hardwired, we had control houses out there. When I first got out to the field, everything was really off. Number 4 galvanized line, the control house was as long as this right here. They were about half as wide. And there's a program. And they were actually they came in and replaced all the control relays with PLC. They just lined up. They said you could power it almost out. So 90% of the relays in there is for control. So the control relay, what's the control relay? The relay is eliminate a sensor that's got one contact. In the PLC program, I can keep to the 100 times. So eliminate hardware, eliminate, replace the software. And the main language is what? Ladder. So if you've had PLCs and they and people want to know which one you need to take first, it don't make any difference. You take motor control first, it makes PLC. If you take PLC first, you take motor control. Here we're going to be hardwiring our program. Here we're going to be PLC program. So what we would do if I was going to set this up, we would still have to have these, because these are motor starters. They would be out in the real world, so they're going to have contacts in the power circuit. These contacts right here are programmable, so that means your motor starter would not have to have any auxiliary contacts on it. So all the contacts. Well, how do we get stuff in and out of a PLC? Well, we have what we call input ports that we connect our inputs to, and then we have outputs that are used to run loads outside the PLC. So your contactors would be outside the PLC. Your motor starters would be outside the PLC. Your push buttons would be outside the PLC. But all the other stuff would be programmed. I got one right here. I could hook it up and we could program this thing. They're not hard to program. So this would be the thing. This would be the program. This would be the actual ladder logic. This right here would be the program. This is a symbol for an output port. That means these guys right here would actually control an output. It's very similar, right? We don't have push buttons inside the program. We got a symbol that represents the push button. Does that make sense? The push button would actually be connected to the PLC, and I think that's in the next diagram. So this would be the connection of the circuit. So we hook up all the inputs to what we call input ports. We hook up all the devices that's going to operate in the power circuit. We'll hook those up to output ports. And then what we do is program reads the input port, runs it through a program, and updates out. Turns out the phone. This will eliminate a lot of hardware stuff. Hardware stuff. Plus the next advantage of taking a push button that's got one contact. You can use that contact any way you want. So it eliminates these bad lines. So this is the push button. And this controls 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9 contacts. If this isn't a PLC, what I would do is I would use one push button, one contact, and I would just duplicate that contact throughout the program. So this allows us to use solid state sensors. Some y'all got that right now. Solid state sensors, contact. And then a PLC program, I can use 100 contacts to go that one. It's really, really eliminates hardware. They interface is a lot easier. They're trying to figure out how to wire all these push buttons into the circuit that we have to do in a motor control circuit. It's program. Very, very, very simple. So we take our X-ray off our PLC, we'll put the program in there that does this. And I'm not gonna hook up relay. What we'll do is we'll just turn on lights. So y'all go ahead and take a 10-minute break and we'll come back and I'll do this for you. Well, I could do it with a simulator. I'll do it. This is a programming application called RS Logic 500. It's an it's used to program Allen Bradley Micro Logics PLCs. It used to be used to program this guy over here. This is called a 500 level PLC. These are now obsolete. The newest version they have out is called RS Logic 5000. It's used to program their compact logic levels of PLCs. So, but it's Allen Bradley, so you can't use one application to program different people's PLCs. So this is why most companies like to get the same brand of PLCs. If you got multiple different PLCs, then you'd have to have one application for every brand that you have. So Allen Bradley is the predominant program controller in the United States, but we're getting a big influx of Siemens PLCs here in our area because of all the German companies. So over in Europe, the biggest PLC manufacturer is a company called Siemens. And I think some of these relays that we passed around were actually Siemens PLCs. So we'll just create a new program, and the first thing it's going to ask me is, since this thing can program a lot of different PLCs, it's asking me which PLC I'm trying to program. And this is a MicroLogic 1000 Series B. And here we go. So we start off with an N rung. It's put in there automatically. One big thing different in PLCs than motor controls. Motor controls, we number lines. PLCs, we number rungs. Big difference. I'm going to bring out a different rung right here. And it looks like I need one rung. I'm going to put a contact there. And this is going to be connected to an input. And then I'll put a down drop. So I'm doing the circuit that's, and I'll drag this over right there. And then down here, we're going to put in another down drop. We probably need to put something in here. I'm going to put a contact right here. And I need a contact right here. This is going to be the stop button right there. Y'all see the circuit I'm doing? I think it's in your book. So this is the circuit we're doing right here. They've got the stop on the right-hand side. I'll put the stop on the left-hand side. This is the way they like to do it, and this is the wrong symbol, by the way. That's a common mistake that you make, and okay, then what we'll do, we'll bring down another one of these. put it right there. Drag this over to here. And then I think we need another one. Okay. And then this will be a stop. This will be the C-land. And then these are our outputs. Yeah, we can do it like this. We can't have another two outputs over here. So what I'll have to do is I'm going to put in another rung right here. And then I'm going to put the same stop button right there. So that'll be the same thing. I only got one stop button, guys. And then I'm going to come over here and put this right here. Put in a down drop. Slide it over to here. Then we'll put right there. Then I'm going to come over and put a coil. Okay. So this is going to be my stop button. So what we have to do is we have to assign it to a physical address. So I'm going to put I. What do you think I stands for? Input 0/0. And then I'm going to call this stop. And then I'm going to come over here and put this at input 0/1. And we'll call this forward. Then I'm going to come over here and put this at output. So this is going to generate an output 0/0. And I can't call it forward because I've already given it that name. So we'll call it forward. And we'll call it M1. Okay. Then I'm going to come over here. This is not a physical wire, but I'm going to give it the same name, forward M1, and it automatically fill in all the information for me. I need to put a normally closed contact right here. And I'm going to put a normally closed contact right here. How long would it take you to wire this up? I'm going to come down here and repeat this one because we can't do it the same way. But I'm just going to call it stop. So it's got the same address as this input right here. So it's working at exactly the same. But I'm only got one stop button. But I can use it as many times. I can use contacts as many times as I want to. This button right here, we'll call it reverse. I'm sorry, we'll assign it to a different input 0/2. And we'll call this forward. Huh? Oh, I couldn't do it. Notice it wouldn't let me do it. Why? Because it's already been assigned. So we'll call this guy reverse. Then this guy I got to give a different name. This is going to be equal to RED M1. Oops, messed up, guys. This is going to be output. Keep going around. Output 0/1. I got to give it a different address, but I've already given it a symbol. Then down here, I'm just going to control this by RED M1. Over here, I'm going to control this by RED M1. And over here, I'm going to control this by FWD M1. And that's the circuit. How long would it take y'all to wire that circuit? How long did it take me to program it? Check for errors. Everything looks okay. So this is the same program, except they put the stop button. So here's my interlock, but these are not done by auxiliary contacts. These are done in software, right? You understand that? How many times can I use my stop button? Even though I got one stop button, I can simulate as many contacts as I want. I just give them all the same name. So what we do is we give them names. RSLogic 500 calls them symbols. All your other ones calls them tags. So once we get, and the analogy I use is like your contact your phone. How do you know all the phone numbers of your contacts? Because you assign a name, right? You assign a tag. So what we do is, we put the original phone number in there, and then we can use it, as long as we use the same tag, it automatically inserts all the information. People require, our site is optional, but all your people do that. So down here, I didn't actually type it. So here's the address. This is output 001. And if we come over here, if I can get my camera up. Not this camera, Rich. My other camera comes up, please. There it is right there. Let's see if it'll focus in. Didn't switch here. It's still trying to. Okay, here we go. It's not going to focus. So here's where you actually wire up your actual true input devices and your output devices. So here's where I wire inputs. Usually inputs on the top, outputs on the bottom. In PLC 1, you draw how you hook it up. In PLC 3, you would actually hook it up. These actually run down to these true output ports right here. So this is switch 0. So these are the switches I'm using. 0, 1, 2, 3, 4, 5, 6, 7. I think we're just using on this side. These are outputs. So instead of, if I wanted to run a relay, I would just connect it up to these things. Technically, we would do it on the PLC, but this is the trainer, and I needed to block that. So let's look at our program. First of all, what I have to do now, I have to download it into the PLC. And it's going to give me a bunch of stuff popping up here. Got to give it a name. What figure is that in the book? That's okay. We're going to download the program. Going to switch to the run mode. Tells me my communication don't match. And while automatically it shows me, and this guy helps you troubleshoot. So any of the green, it's allowing the information to flow through it. So that's my stop button. So both stop buttons are already closed. Switch 1, so switch 1 is the forward. Of course, on your real life, you would have legend plates on this, right? So here's switch 1. I won't just touch it. And it shows me, the green shows me that the path is going through here, over here. This relay here is energized. And if I look at my output 0 should be turned on. And this is where I would have my relay connected on the outside, right? You understand that? I can come over here and do my reverse button, which is 2, and you can see it's making. What's keeping my reverse from energizing? This interlock right here, right? Yeah. But see on this one, so here it gets rid of using even a meter a lot. All this is programmed in. If I wanted to make a change to it, I can make it in software without going out there and rewire it. So what do I need to do? I need to hit my stop. So here's my stop. Drops out. Then I bring it back in because it's supposed to be a push button. Now when I hit 2, Rich, I did the wrong one. Stop button. Now when I hit 2, my bottom one energizes. If I look at my outputs, output 1 should be true now. It is. So this one's off, this one's on. I'm sorry it won't focus in. And this is, so that would actually energize the relay. So how long did it take me to wire this up? And so, so what we can do is PLCs eliminate a lot of wiring. The only thing I got to wire up is my outputs and then my switches. This right here is simulated. That's not actually a contact. this is not a true contact, this is in software. So now I can buy contactors, I mean, I can buy overload, I can buy movie starters, now I can contacts, like that. I'll save a ton of money on wire. The only thing I gotta do is wire up and put it wire out and create a problem. Make sense? So guys, that's the way of that goes. So those plants now, get out there, it doesn't go away with the power contactor, y'all understand that? It doesn't go away with all your controls. All your decision making now is that program, it's not done with the hardware. But still, see how easy it was for you to program that, because all these is matter on, that you don't have all these symbols. You don't have a symbol for temperature switch, you have all these symbols as part of your relay on it. You've got a normal open and normal close. You can control, you put the column down, close, and open. So, what do you think?
Is that why the stops there have normally open contact?
No, they're not going to go to contact.
That's what I mean, visually.
Usually they are. That's what we call a exam close. It's true, it's close. So that's a big difference in field 50. So normally, when we have a quote did it wrong, but the guy in the quote did it wrong. So if I was to change that, if I was to change that to exam open, I'm sorry, this is the exam close. If I was to change it to exam open, then I would use the direct on the open push button to stop. Now, what's wrong with the normal open push button? Why is the normal open push button hard? It's wire rate. Yeah, so wire rate should be able to stop it. So, but what happens is simple shifts over inside the system. And this is one of the main things that we have problems with. People coming from other, so they want to use a symbol for a normal contact, but it's not a symbol, that is not the normal. And in the stop button, close. The other ones are all open. So let's change it back over to the symbol. So I'm gonna go offline so I can change programs. Let me use my mouse, it's a bit faster. So the only way you can change the program, you have to go offline with the processor. So when you're online, you're actually monitoring what's going on. And I'm gonna come up here and I'm gonna change the instruction type, and I'm gonna change this to an examine if open. And it gives me the symbol of that. Check it for errors, and then I'm gonna download it. And I'm using a normally closed push button there. Well, I'm using a switch simulating that. And now it shows us what? Now it shows it's false. This one, I'm using the examine if closed instruction, it shows it's true. So it means I would have to change this to a normally open push button. And now, if my wire broke going to my motor, going to my push button, I wouldn't be able to stop the system. Let's do that. And that gives people in motor controls problems because they see that symbol as a normal closed contact. So this thing is true, it's open, this thing is true, it's closed. Now these are just contacts. These are normally closed, normally open contacts. These are not connected to inputs. But we don't worry about these. It's just those inputs we have to figure out what we need to use that. No big deal. So it took me, 10 minutes to program this. Probably take me maybe, depends on where your options are. It's all you gotta do is wire input and wire out. So you don't have to wire control circuit. All you gotta do is wire input and wire out. Any information that has to come in from the outside world that is not that you control has to be controlled by the outside. So right now. I was searching for, I had to go out and, but this is why these things are dominant. Okay. You still don't have relays, you guys do not eliminate the relay. And what determines that you relay knowledge, you know, whether they, cost. It's cheaper to do all the relays, they'll use the relay. Cheaper to do one thing than others.
We did have one customer that wanted us to do a relay panel, all relays, and it was probably 150 relays, because the guy working on it didn't understand PLC.
So it probably cost them a lot more too. Relays are not cheap, especially contactors. These guys get up in the $200, $300 range for contactors, depending on how much, and motor starters with overloads on them. So PLCs, depends, you know, you might spend $1,000 for a PLC, and then you spend $18,000 for the programming application. So these people don't make money on their PLCs. They make money on the application used to program it. Luckily, we're an educational institution. We register this software right here. It gives us the complete suite. They call it Suite 1000. In fact, 5,000. We get that entire suite for about $250 a year. So that's PLCs. This is the same circuit, guys, and y'all can see one of these are really dominating, right? Let's do that. So if I wanted to change something, how long did it take me to change that from a examine if open to examine if closed? Yeah, 30 seconds. If I went out there to the real world, I'd have to do, on a relay logic, what would I have to do? I'd have to rewire the dang thing. So this is pretty neat about a PLC too. So questions? Questions on reversers? Yes, no? Programmable controllers simplifies it, so this is all you'd have to connect up. All you have to do is connect up your inputs and outputs. But see, this guy right here uses a normally closed push button. And this happens all the time. In his diagram, that's his stop button. He's using an examine if open instruction. It would never work. Somebody would have to stay out there the whole time and hold down the stop button. That's what I'm talking about. So this is the PLC program. He's using the examine if open. And then over here, he's using a normally closed push button. This is even done in our PLC book. The guy that wrote the book on PLC does the same thing. He'll look up a normally closed push button and call it stop. And then in the PLC program, he'll use an examine if open instructions. So that's the biggest problem if you take the PLC class. This is another thing I wanted to make sure you saw. This at the bottom, this is the wiring diagram. The one at the top is the ladder diagram. Everything is still there. But you have to figure out the circuit. So here's your relays. This dashed line means all these push buttons are in the same enclosure. But what a wiring diagram tries to do is try to show you how all these lines are physically oriented. Most of it gives you their location, not necessarily. I don't know who doesn't have it. All I know is that they're all inside the same. Now, we use ladder diagrams a lot for the power circuit. I mean, for the actual circuit that's controlling stuff. And this is going to be true in your book. So here's our 3 lines. So this is the way we would hook up our motor. So this goes to L2. So this goes to, so at the top of your contactors that came around, the 3 contacts on the top are called L1, or 3 connections on the top are called L1, L2, and L3. And this is your 3-phase. This is not your L1, L2 on your control transformer. This is that 208 you got up there, right? You understand? Now down on the bottom of the contacts, these are going to be called T1, T2, and T3. And this would be T1, T2, T3. So that's the output side. So normally, according to National Electrical Code, power is supposed to come into the top and control is supposed to come out at the bottom, right? So your panel box at your house, where does the power come in? Where did it coming out off the transformer? Where does it come in? It comes in the top, right? You understand? So this is so everything goes the same way. So up here, we'll use on our contactor or on our motor starter, the top ones are going to be labeled L1, L2, and L3. At the bottom one, where we make our screw connections down here, they're going to be labeled T1, T2, and T3. So you know the difference, right? You understand that. And of course, what are they doing? So here comes up here. So L1 goes to L1 on both of them. L2 goes to L2. L3 goes to L3 on the top. Now on the bottom one, this comes over here. Oops, that's the relay. This comes over here. Right? This comes straight through. And over here, notice what they do. Over here, L3 on this one goes back to what? I'm sorry. L1 on this one goes back to L3, and L2 goes to L2, and then L3 goes to L1. So where do you do your wire swapping? You don't do it at the top of the relay. You do it at the what? At the bottom, on the T1 sides. And this is going to give people problems too. In fact, we're not going to let you hook up the motor until you can see if it's wired up correctly. So this is what you're going to do to wire up your motor. We use that to wire up your control circuit. We do not have ED reversers. So this is a true reversing contactor. So you got two days side by side. Wire it forward. Wire it. It's got one set of overlays. So we do not have that in our lab. What we're going to do is we're going to we don't have reversing contactors. We're going to wire these and reverse. Instead of having one set of overlays, and the correction is made in the lab book, by the way. We're going to break this line right here, and then we're going to come over here, and our circuits are going to be wired like this. We're using two individual motor starters. So we don't have any reversing contact. We got some, but not enough for the class. So this is going to be our control system. You understand? Which wire don't you have to run? You're not going to have to run this wire right here. It's internal. But you got to make sure that the overload contact goes toward the L2 side, right? We'll see how anybody does that wrong. Are y'all okay? Any questions on reversers? We're going to reverse a three-phase motor. And like I said, in the lab book, what we're going to be concerned, we're going to use this to wire the motor. And we use that to wire the circuit. Everybody okay? Yes, no? So guys, we got one option. What I want to do, I know these classes get very long, but the only thing we got enough to go over is time. Go ahead, 2 hours, 2 hours a day, so hopefully we're ready. And we can have the rest of the session. So we're still pretty fast. By the way, the reversing circuit, and I'll give you the lab number. Part of our accreditation is we have to have what we call student learner outcomes. And one of our student learner outcomes for this program for ILC, everybody in ILC has to take motor control and do reversing that. I want to go ahead and go to the, first. Okay? That's not true. I want to go to the other route first. Okay, where I was over. And then go to the reverse line there. Okay? By the way, I was driving my house and I'm very, very relaxed on homework. I'll go ahead and turn it to homework. What homework class we're gonna do. What I'm gonna do, guys, is I'm gonna give y'all until Tuesday, next Tuesday, to do all the homework. If you don't turn it in, I won't set it. Okay? By the way, I think I have those, I can run those off for you. If I need to. Okay, timers.